Look through your window right now. That perfectly clear sheet of glass separating you from the outside world started as ordinary sand, buried in a quiet desert. Every year, the world produces over 200 million tons of glass. It is in your phone, your car, your building, and even inside the fiber optic cables delivering this video to your screen right now. Yet almost nobody knows how a simple grain of sand becomes one of the most versatile materials on Earth. The journey begins in specialized silica sand quarries. Not just any sand will work. Glassmaking demands an extremely pure form of silicon dioxide, with purity levels above 99%. These rare deposits formed over millions of years under ancient geological conditions. Major quarries are found across the United States, Australia, and parts of Northern Europe, where the Earth produced vast reserves of high-quality quartz sand. Massive hydraulic excavators and front-end loaders scoop thousands of tons of raw silica from open-pit mines every single day. The sand appears almost white, far paler than ordinary beach sand. Each grain feels coarser and sharper, because it is a tiny crystal of nearly pure silicon dioxide, the fundamental building block of all glass. After extraction, the sand goes through a rigorous washing and screening process. Water jets and vibrating screens remove clay, iron particles, and organic impurities that would otherwise discolor the finished glass. Even the smallest trace of iron can turn clear glass into a greenish tint. That is why purity control begins right here at the mine, long before the sand ever reaches a factory. Once cleaned and graded, the silica is loaded onto freight trains and heavy trucks. It travels hundreds of miles to reach enormous glass manufacturing plants. Some of the largest facilities in the world run non-stop, 24 hours a day, 365 days a year. Their furnaces never shut down. A single furnace campaign can last 15 to 20 years of continuous operation before the refractory walls must be completely rebuilt. But raw silica alone cannot become glass. It must be combined with other essential raw materials. Soda ash, chemically known as sodium carbonate, dramatically lowers the melting point. Without it, pure silica would need temperatures exceeding 2,000 degrees Celsius to melt, making production impossibly expensive. Limestone and dolomite are added to improve chemical durability. These ingredients prevent the finished glass from slowly dissolving when exposed to water over time. Inside the plant, the raw materials enter the batch house. Giant silos feed precise amounts of silica, soda ash, limestone, and other additives onto conveyor belts. Computer-controlled systems weigh every component down to fractions of a kilogram. Even tiny variations in the recipe can change the color, transparency, or mechanical strength of the final product. Recycled glass, known as cullet, is also mixed into the batch. Modern glass plants recycle enormous quantities of broken and discarded glass. Cullet melts at a lower temperature than fresh raw materials, significantly reducing the energy required to run the furnace. It also extends the operational life of the refractory lining inside. The blended batch travels by conveyor into a massive regenerative furnace. These furnaces are engineering marvels, lined with heat-resistant bricks that can withstand years of continuous exposure to extreme temperatures. Inside, the temperature soars above 1,700 degrees Celsius. That is hot enough to melt steel. The raw materials slowly dissolve into a glowing river of molten glass. The liquid appears as a blindingly bright white-orange mass, radiating intense heat that can be felt from dozens of meters away. Workers in full protective gear monitor the process from behind shielded control stations. As the molten glass moves through the furnace, trapped gas bubbles gradually rise to the surface and escape. This critical stage is called fining. It ensures the finished glass will be completely free of air pockets. Even one tiny trapped bubble can weaken the structural integrity or distort optical clarity, making fining one of the most important steps in the entire process. Now comes the most revolutionary stage in modern glass production, the float process. This technique was invented by Sir Alistair Pilkington in the 1950s, and it completely transformed how flat glass is made worldwide. Molten glass flows out of the furnace and pours onto a perfectly level bath of liquid tin. Because glass is lighter than molten tin, it floats on the surface. It naturally spreads into a perfectly flat, uniform ribbon with mirror-smooth surfaces on both sides. No grinding or polishing is needed. The tin bath does all the work. At the entry point, the glass is still around 1100 degrees Celsius and moves like thick honey. As it glides along the tin bath, it gradually cools and solidifies into a continuous ribbon. The thickness is controlled entirely by speed. Pull the ribbon faster and it stretches thinner. Slow it down and the glass grows thicker. Modern float lines can produce glass as thin as 0.4 millimeters or as thick as 25 millimeters using this single principle. By the time the ribbon exits the tin bath, it is cooled to roughly 600 degrees Celsius. It is now solid enough to be lifted onto ceramic rollers without leaving any marks on the surface. But the glass is still dangerously hot and filled with internal stress. The ribbon enters the annealing layer. This is a long, precisely controlled cooling tunnel stretching several hundred meters. Inside, the glass cools at an extremely slow and carefully calculated rate over several hours. This gradual cooling process relieves all the internal stresses that built up during forming. Without proper annealing, the glass would be so fragile it could shatter from the slightest touch or the smallest temperature change. After annealing, the glass reaches room temperature and enters the cutting section. Automated systems equipped with diamond-tipped wheels score the continuous ribbon into individual sheets with perfect precision. High-speed optical scanners inspect every square centimeter of the glass surface, detecting flaws as small as a fraction of a millimeter. Sheets that fail inspection are immediately rejected and fed back into the system as cullet. But standard float glass is not strong enough for every application. Car windshields, shower doors, smartphone screens, and skyscraper facades all demand glass that can withstand extreme mechanical and thermal forces. This is where tempering comes in. Glass sheets are reheated to approximately 620 degrees Celsius in a specialized oven. Then, powerful air jets blast both surfaces simultaneously with rapid cooling. This creates a compressed outer layer and a tensioned core. The result is tempered glass, 4 to 5 times stronger than standard glass. And when tempered glass does break, it crumbles into small, blunt granules instead of dangerous razor-sharp shards. For maximum safety, some critical applications use laminated glass. 2 sheets of glass are permanently bonded together with a thin interlayer of polyvinyl butyryl, known as PVB. When laminated glass breaks, every fragment remains stuck to the interlayer. Nothing flies outward. This is why every single car windshield manufactured anywhere in the world is made of laminated glass. Modern glass factories also apply specialized high-performance coatings. Low emissivity coatings reflect infrared heat radiation, keeping buildings warmer in winter and cooler in summer without any additional energy. Self-cleaning coatings use ultraviolet light from the sun to break down organic dirt on the surface automatically. Anti-reflective coatings maximize optical clarity for display screens, camera lenses, and precision instruments. After passing rigorous final inspection, the finished sheets are carefully prepared for shipment. Giant vacuum suction cups lift each sheet and place it onto specially designed wooden crates or transport racks. Every sheet must be perfectly secured, because even the slightest vibration or contact during transit could cause invisible micro-scratches on the polished surface. From factory floors, the finished glass travels by truck, train, and ocean-going cargo ship to construction sites, automotive assembly plants, electronics manufacturers, furniture makers, solar panel producers, and thousands of other industries worldwide. Take one more look around you. the windows in your building letting in the sunlight, the screen you are watching this on right now, the mirror in your bathroom, the lenses in your glasses, the fiber optic cables beneath your feet carrying the entire internet. All of it began as a simple grain of sand in a quiet quarry. From a desert floor to the structures that shape modern civilization, this is the journey of glass.